So the historical context. It's important that you understand that the very perspective or some basic assumptions that you start with can really influence how you think about global warming. So I'm going to just real quickly review the basic earth science involved, but then suggest that we might think about the human species as a natural phenomenon, as something that the earth came up with, but that it's a relatively new phenomenon. So the humanity is kind of a new behavior of the earth that started relatively recently, and it's not really field tested. It hasn't been around long enough to know what kind of consequences it's going to have. So we'll have that deep historical perspective, but we'll also think about how things have changed since the advent of the Industrial Revolution, which some people call the fossil fuels revolution, because it was largely the use of fossil fuels that made the industrialization of the global economy possible. Okay, so first point. Global warming is something that we certainly need, or else we would all very quickly freeze to death. So the sun throws out a bunch of heat, some of it bounces off the planet, and if we didn't catch some of that heat as it bounced off the planet, there wouldn't be enough absorbed and we would all freeze to death. So it's good that there are greenhouse gases like carbon dioxide, nitrogen, and methane that are going to bounce back some of that radiated heat to the planet. So this is like a blanket that you keep on at night to keep you warm. But the problem is we've been steadily adding to these greenhouse gases, so this delicate balance that's maintained the temperature as it's been for thousands of years is getting messed up, and we're slowly adding more greenhouse gases here, so that we're slowly heating up the planet, and that's going to have some nasty consequences. Okay, second point, we want to think about the population explosion, and I'm going to show it to you in one of two ways. Here's the short view. If you look from 1750, so that's about the Industrial Revolution, up till 2000, and then they're projecting out more billions of people being added. Not so much in the developed countries, but in the less developed countries. There's this kind of population explosion. But if you look just from this perspective, it doesn't look that bad. But if you adopt a longer view, kind of from the perspective of the Earth, and go back into the Stone Age, 2.5 million years ago, it starts off pretty small in terms of human population, and then it starts growing. And you understand here that there is this spike that occurs, which looks like somebody's having a heart attack, right? There's a little dip here at the Black Death during the Middle Ages. And then there's this huge growth. And so if you project out to 2025, we're going to have lots and lots more people, billions of people on this planet. So one idea or one metaphor that might help you grasp this is there's the 6-day week model of evolution. Now this is not a creationist model, but it's taking that idea of 6 days as a frame of reference that we all are accustomed to because we understand how long a week is, and that makes kind of sense to us at a gut level. So let's do this. Let's start imagining that life came about in the most basic kind of little blob of stuff form on Monday morning at 12:01 or 12 midnight, and then it keeps going and going and going until the present day, which would be Saturday night at 12 midnight. So the question is, when do modern humans arise? In other words, Homo sapiens sapiens. You might be surprised, or you might think, well, maybe they came about like on Wednesday or Thursday or Friday. It turns out that they didn't come about until 11:59 and 49 seconds. In other words, with only 11 seconds left in the week. And recorded human history, so from the Code of Hammurabi and original civilization in the Near East, that has only been 2/3 of a second. So that suggests to us that when we think about the world as being kind of humanity's playground, humanity is a pretty recent addition to the ecological mix that has comprised the planet. And so it's as if you're driving in a car and everything's going fine, and then all of a sudden you hit the gas, and for the first few seconds everything seems to be going okay. But that's really not a good indicator of the long-term consequences of hitting the gas and holding it to the floor, because just a few seconds, you won't see the full long-term consequences of it. So to make that point, one way of thinking about this is humans equal a certain kind of drastic change. So going back not too far, a little before the 1800s, up to the present day, you can see a pretty drastic decrease in the number of acres, millions of hectares of tropical forests. More generally, if I were to ask you what percent of all the forests that were once on the planet are still on the planet, we're down to 50%. So we've already lost half of what was on the planet. And what that means is when you and I are born, we look around and say, okay, there's about this many forests. And then 10, 20 years go by and we're like, yeah, all right, we still got a lot of forests. But we don't realize our ancestors have already done a lot of chopping and burning and clearing of land. And that forest is important, obviously, because that's where you have the capacity to absorb carbon and keep it out of the atmosphere. And the more you cut down those forests, the more you're going to put it up in the atmosphere. Okay, so a few more background facts. The U.S. is the leader in fossil fuel production. You can see that here. We handily beat any other country. And that's a problem. But if you look here at India and China, they're not putting out nearly as much as us. But let's look at this. They have a lot more people than we do, some 3 to 4 times as many people, each of them. So we're around 300 million now, and India and China, they're putting it over 1 billion people each. And this is in 2006, so these numbers are out of date. And there are already more people there. And the idea is once they start living like Americans, wanting to eat meat, wanting to drive cars and live in big houses, the impact on the climate is going to be drastically larger. So let's shift gears now and think about time in a shorter frame, when the Industrial Revolution began. And I have the arrow here pointing, somebody goofed up. It should be pointing a little more up here at 1750. But at any rate, you see there's this beginning of a curve where it's flat in terms of carbon emissions, and then it starts going up. So carbon emissions, that comes from burning oil, burning coal, gasoline, all that stuff. And as the emissions of carbon go up per year, big surprise, the CO2 concentrations, carbon expressed as a gas in the atmosphere, goes up. And then pretty closely, what's tracking that? Temperature. Now there's yearly variation based on El Nino and other kinds of things, but by and large, as carbon emissions go up, carbon concentrations go up, which causes temperature to go up. So what do we mean when we say fossil fuels? We mean overall, here's the total. You can see it's still clearly going up. But we can break that down into petroleum, which we get gas that drives our cars, we get coal, and we get natural gas. And then down here also is cement production, which most people don't realize, but that also contributes substantially to carbon output. So it's still increasing, and these are some of the different kinds of carbon that we have. And then what does that mean? That means that we're putting more greenhouse gases into the atmosphere. So here we have carbon dioxide and methane, both are greenhouse gases. And we see that from back in the day, in the 1700s, it's starting off and then we're increasing drastically, and the same thing with methane. And to get an idea of what the temperature was back in 1700, 1800, they go to cold places where there's a long record of compressed ice. And if they dig down, they get samples that go back in time, so to speak, so they can look at what the air was like at these different years, and they can then plot what carbon is and what methane is. And then more recently, we're measuring things from observatories. So like there's an observatory in Hawaii that tracks the carbon in the atmosphere. And combining these two data sources, we can plot these curves. So if we go back even further, you can see that it's pretty steady for a long time. And then we have around 1800, after the Industrial Revolution starts off, we start getting this increase. And this is showing data collected both from Antarctica and Greenland. And it's important that you have both of those because one of those is on the top of the planet, so to speak, Greenland, and one is near the bottom, Antarctica. So that suggests, because they track together, that it's a global phenomenon. It's not a local aberration. So more specifically here, and I don't think I gave you these slides, but they show the same pattern. You've got the greenhouse gases from the ice cores and then the modern data combined. And if you go back 10,000 years, it's flat, 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 and then boom, there's the spike. Again, we want to understand that there's a difference in terms of what a long time is. We might think about this scale up here as being adequate, but from the scale of the Earth, we can see that this is much more, again, like a heart attack. So we see this with carbon dioxide. We see the methane going flat and then spiking, and then we see nitrous oxide, and nitrous oxide that comes from artificial fertilizer made from nitrogen. And so primarily different kinds of farming practices that produce that. Again, but largely flat, and then boom, this spike. So summarizing the historical stuff there. One, you've seen this population explosion. Historically, it's happened, and with China and India and other countries with booming populations, you're going to see even more carbon output. And we want to think about humanity as a new phenomenon on the planet, try to step away from our human-centric view and think about from the planet's view and recognize that humans have really made some big changes, especially since we've got to the Industrial Revolution. And then we showed you various graphs there to show you what's actually happening with the greenhouse gases, and that there's been an explosion. From the Earth's perspective, it's a sudden onset of some pretty drastic changes. All right, next we're going to turn to the evidence and consequences. I think I'm going to stop here at this point and put this in a separate lecture so the file doesn't get too big, but this is where we'll pick up. Okay, this is the second part of our global warming lecture. Now we're going to look at the evidence for and the consequences of global warming. So what kind of evidence do we see? And most importantly, how does the evidence fit together? So sometimes skeptics will point to one specific data point and call it another question. But what I want you to be able to do is, if someone asks you, give several different kinds of evidence for the overall picture of what's happening and show folks or be able to explain how those things are connected. And then we'll look at some of the possibilities going forward. Okay, so first of all, it's clear that there is an increase in global temperatures. So this includes both the surface temperature on land and water, and it's comparing it to an average of this whole time. So you can see that we used to have lower temperatures, the temperatures are getting higher, and there's this trend towards increasing temperatures. So from year to year there can be some variation, but overall, given this long record, we can be pretty confident that temperature is going up. Second, sea level is rising, and you can look at over roughly the same time period, sea level in terms of millimeters. We're starting out here at zero change, and then it's picking up. And interestingly enough, some people are arguing that the rate at which it's changing is increasing. So not only is it going up, but it's going up at a steeper clip. In other words, we're like picking up speed. Key point here is that the numerous points of evidence converge. We should expect global average surface temperatures going up. That's what we see. Sea level should be going up. That's what we see. In northern hemisphere, snow cover should be going down. That's what we see. Fourth point, the models are accurate. So in other words, when they have these computer simulations and they plug in a bunch of different data points, and here are several of the different different models, and they plot them, they're able to both explain temperature changes in the past and explain temperature changes in the future. And so this here is a certain data point, 2015. So during this period between, 2012 and 2014, it looked like the models were not being accurate, and that they were overall over-predicting the that temperature wasn't going up as quickly as they had predicted. But with this 2015 data point, it's again back on that track. And so the short story is the models do predict accurately, within some error, that what the temperatures are going to be and what they've been. All right, fifth point here is the vegetation is shifting north. So stuff that didn't used to grow at a certain latitude is now growing at that latitude. So if you look here, there's certain bands that now stretch farther up. So that means the reason those bands are shifting is it's getting warmer at any given latitude. So plants that used to have to be a little bit closer to the equator can now get by being a little further away from the equator. You also see the same phenomenon or similar phenomenon in that vegetation is shifting higher. So trees might have stopped at a certain point, but now that as you move up in altitude, temperature goes down. If the temperature is increasing, they can start creeping up and up to higher altitudes. Point 6, there's more extreme weather events. So somehow I missed the date here. Looks like it's, but the website is 2014. So it's the change in heavy precipitation. So you can look in all these different regions in the U.S. We've seen more and more cases where there's storms that bring a ton of moisture. And if you look at the trends over time, going from the 1900s up to the 2000s, again, we see this clear increase in terms of these heavy precipitation events. So these can be heavy thunderstorms, heavy snowfalls, heavy hurricanes. So ironically, when it snows a lot in the winter, there's some skeptics that'll say, "Ha! That shows there's no global warming." In actuality, that is exactly what's predicted, that you're going to get more, because of the warmer air, you're going to get more precipitation events. Point 7, the glaciers are retreating. So I think this is at Glacier National Park. I'd have to double check that. But you see some folks here, and there's a cave, and then, wow, by 1988, it's all gone. This is in Alaska, the Muir Glacier. It's there. And then now all this area has retreated until it's only back up in there. The Alps, we started off with a slide from the Alps. Here's another one. There was all this huge glacier here, and now that's all disappeared. This is another one. I think this is in Alaska. I'm not positive. Here's Mount Hood. This is in Washington. You can see lots of snow and then not so much snow. Okay, point 8, you're having, this is still melting, but now we're talking about what's going on at the poles. So if the Antarctic ice shelves are melting. So the way the Antarctic works, there's land here, but then there's these ice sheets that extend out over the water, and some of them are beginning to melt and break off. So I'll show you, here's the Larsen B ice shelf. I'll show you that in more detail. So here's in January, and then in March, this is where the ice shelf was, and then what you can see here is all this area broke away, and it's roughly the size of Rhode Island. So in other words, these are huge chunks of ice that have broken off and will break off. You can also see melting in the North Pole. So in the North Pole, it expands and shrinks. The ice cap does, depending on the time of year. Obviously, in the winter, it's going to be more expanded, and the summer is going to shrink back. But the extent to which it's shrinking back is getting more and more pronounced. So this was the boundary of the ice in the summer in 1979, but you can see it's gone in a lot past that. So here's another way of looking at it. This is the extent of the Arctic sea ice in 1984, and here's what it was in 2012. Here's another figure that shows you where it was in 1980. That's the red area. And then the pink area is where it was in 1998 and 2012. And so obviously the big problem here is the North Pole is where Santa Claus is, and that's where all your presents come from. So you can look forward to some depressing Christmases. But in actuality, one of the depressing things is that it's having a huge impact on the species that live there. So polar bears are drowning. They're finding it harder and harder to find food. They'll flow out. Their fishing strategy is to swim out to these different ice flows, but now they'll swim out there and they won't find anything, and so they're more likely to drown. Some other bizarre things that are happening: the fabled Northwest Passage that different explorers had searched for to try to get up around North America, those passages now exist. So in the summer, you can navigate from Finland and Sweden over here to the United States. It's a much quicker route, obviously, because you're just going across the top. It's not covering as many miles. And so that's having a number of commercial implications. Another point is that, ironically, because we have burned so much oil and gas, we are making more oil and gas available for harvesting in the Arctic because we have melted off some of the ice caps that were had before covered up those deposits and prevented access. Some more melting stuff. Greenland, which crosses into the Arctic, is experiencing a similar thing where in the summers you get more and more ice melt. So this is a neat 3D graph here where you can see the 92 melt line is significantly lower than the 2005 melt line. So what you see from year to year is more and more of the snow melting each summer. And you can see this pattern in the trend line there going up to 2008. And here's a graphical quantification of what's going on. So I have the yellow line pointing here to the average, which is the dotted blue line. And you can see in some recent years it's gotten pretty extreme. So 2012 was a particularly extreme year where you had a huge amount of ice melting, and then some other years. But you can see overall they're on this side of the average, meaning that there's definitely a trend in the direction of more melting in the summers. It is a dynamic system. In other words, you're talking not only about how much runoff there is, that's the blue line, but also how much accumulation there is. So because there's more snowfall, because the air is getting warmer, some of that ice is replaced by more ice that falls, but in general, you can see that there is a growing gap where these two things used to be in concert. Now you have more runoff and ice discharge than you do accumulation, and that means you're in danger of having these ice slip away. So here's how this might happen. So you have these moulins that develop, which are holes in the surface of the glacier that where water that's warmer melts the tunnel down to the bedrock, and then this can act like a lubricant and allow this whole ice sheet to slide. Okay, so some of the evidence we have here: rising temperature. I think there was a mistake on your slide where I had the second one labeled as rising ocean temperatures. It should say rising sea levels. Third, there's the evidence converging for the models are predicting accurately. So the computer models are accurate both going backwards and forwards. Vegetation is shifting, weather events becoming more extreme, glaciers are retreating, the Arctic and the Antarctic are melting, and Greenland melting. So if nothing else, grasp that it's a very consistent story with a lot of different characters all pointing in the same direction of substantial changes to our climate and Earth systems. So the future, what's likely to happen moving forward, and what are the consequences? Well, all predictions include warming. It depends on what assumptions you make, but it's clear that in any case we're going to have, at the best case scenario, a little bit of warming. At the worst case scenario, enough that it could be catastrophic. And I'm going to try here to go to a website that the NASA has. Let me see if I can get this shrunk down for you. If we go here to the global temperatures, you can see that there is this schematic where I can start in 1884, and as I drag it to the right, we can see what happens to the temperature differences, and you'll see that it gets steadily warmer and warmer and warmer. I'm up to 1983, 1993, 2000. It's looking crazy, and then it even gets darker and darker. So this is suggesting that many dark red areas are hitting 2 degrees Celsius change from over the last century. Okay, and sea levels are expected to continue to rise. Again, there's different projections. We don't know what's going to happen exactly, but we do know it's going to increase. And depending on the scenarios, there could be enough sea level rise that you would lose whole areas of Florida. And bear in mind, there are millions of people that live here in this area, and that's so we can have a 3-meter rise would knock out that much, a 6-meter rise would knock out that much. So as you might surmise, people like being near the ocean, and so some of these areas that would be inundated would be some of those closest to the water and most populated. Okay, worldwide, it's going to put 10 to 50 million at risk because, like I was just saying, there's a lot of people that live in these island nations and live, say, on the coast of India, the coast of China, Japan. It's just mind-boggling to think about what that